Hello everyone, this is a video lecture for Linear Algebra Chapter 6. We're going to be doing linear transformations. Or just linear transforms, a little bit shorter there. So, let's get started. We're going to do the entire chapter here. 6.1, well, is linear transformations. Let me show you what a linear transformation is by definition. So we're going to say let my V and W be vector spaces. So we have both vector spaces. We have this T, which is the linear transformation, capital T, defined as going from V to W. So this is a function that's going from the V space to the W space. And in practice, sometimes, I mean, in basic things, we could say this goes from the integers to the integers, or the real numbers to the real numbers. We do this all the time with f of x is equal to x squared plus 3x plus 4, something like that. Well, you put in a number, and what are you going to get out of this? It's going to be, well, it's going to be a number. So you put in a number, same number for x, and you get out one number, y. It's the same number, though. It's from number to number kind of thing. Decimal to decimal, integer to integer, that kind of stuff. So, of course, we're talking vectors and all kind of other places and spaces, but those are good, easy examples of what's going on here. So, to make it a linear transformation, I don't think I'll actually spell it every single time. Linear transformation, in particular, is when you have these two particular, I guess, defining attributes. So we have T of U plus V is equal to T of U plus T of V. I'll talk about them here in just a second. So number 2 is that we have T of C times U is equal to C times T of U. Now, given, just kind of like comma for this whole thing right here, my U and V are in V, because they're going to W. They're starting with V, they're going to W. And of course, we have a scalar C. So it's as if we're adding two vectors on the inside means that we can add them separately on the outside. And then the same thing with the scalar multiplier on the inside. You can just basically pop it out to the front here. This is only possible in linear transformations. That's kind of why it's linear by name. And so we're just going to be testing. They're going to say, is this a linear transformation? And we're going to do these two and say yes or no and call it a day. So if this does not work, you say it's not a linear transformation. I'm going to show you examples where they do work, of course. One other thing that they're going to use sometimes, and this is going to be further on, T of, say, like V could sometimes be rewritten as A times V, A times V. So this linear transformation could be written as a matrix, and we're going from one vector space to another. It doesn't necessarily have to be square, but that's just another way to do it, and we'll be seeing that again later on. This is just an example. I think I got a couple from this particular section, but I just wanted to show you some like physical examples. So 6.1.11, I have my transformations going from R3 to R3. So three-dimensional vector, and the function is defined, we're using x, y, and z, as x plus y, x minus y, and then a z. Now, before we move on, they're going to say, hey, is this a linear transformation? Well, notice that we're not like squaring something here. You know, that's kind of a giveaway. I'm not saying that it is necessarily going to work or not. It truly depends on what you're going to do finding these two particular attributes. But, you know, this looks simple. Now, I tried some that were looking simple, and then all of a sudden it didn't work. I want to just show you things that will work, so let's go through it here. So step number 1, first, I guess before we even go into step number 1, I want to actually define what we're going to be doing here. So remember that we want T, U plus V. So we have to define two vectors, and apparently they're three-dimensional space. So what I'm wanting to do then is predefine some variables. So I'm going to say my U is ABC, trying to make my B's look okay. My V is going to be, I don't know, DEF, something like that. And I know also that we're going to have that c times u kind of stuff. So a c, a constant. I'm just going to go ahead and predefine that as well. So A, B, C, D, E, F, G is going to be my scalar later on. I just want to preset them, okay? Let's go and do this. So I'm using parentheses. On my paper, I use the alligator things, the inequality, whatever's. It's just vectors. This is just a vector. It's just a different style of notation. So let's actually do it now. So when I'm saying u plus v, I'm actually saying this stuff plus that stuff. And so we know that these two vectors would line up. I mean, you could line it up like this if you want. I mean, I will do that sometimes so that you could say, oh, look, it's a plus d and b plus e. Be careful here. And then c plus f. Another route, which I wrote in my particular book here, was that I had a plus d, comma, b plus e, comma, c plus f, comma. It's the same thing. It's just, different. It's horizontal rather than vertical. So no problems there. The point that I'm wanting to make out of all this, because these right here are equivalent at this point, I want to actually make the transformation. And so notice that I'm saying that this here is my element x. Okay, so then that's going to go here and here. That's not the entirety of what's going on here. I'm going to actually have to add y to it as well. I think it's easier doing this vertically at this point. So what I'm going to do is say, this is my x, this is my y, this is my z, okay? And so my first thing is x plus y. I actually have to write x plus y. Well, x, a plus d, plus y. Okay, x plus y. And then the next one's going to be x minus the y. And then, of course, just z to z is, well, it doesn't change anything, so you just write that guy right there. I guess you can even use some parentheses if you like. Okay. Awesome. The point that we're going to be wanting to go towards, my goal, is to separate them. I want to do this. So I want to split them up with a plus sign between them. That's the goal. I don't want it just one big matrix vector thing. I want it, to split it up. So what I'm going to do, in particular, is split it up along these lines. I'm going to say a plus b, a minus b, and then a c. And over here, we're going to do the d plus e, d minus e, and then the f. Now, we're just adding and subtracting and stuff like that. I'm distributing this minus sign to these guys. I'm saying, I guess you can rewrite it without the parentheses, a plus d plus b plus e. So then I can rewrite that as saying a plus b plus d plus e. Just however order you want. I'm trying to group them in a way that I want to. Like, scalar addition is commutative, so I'm just going to be adding them wherever I want. And I want to group them like this. That's my decision. Well, it just so happens that this here looks like ABC, my transformation ABC, and then my transformation DEF, which, being more formal, is my U and V. Like, done. So there's my first one. The next one's always much easier. I'm starting with now a G on the inside. And so then if I were to rewrite that, it's GA, GB, GC. And so I go, okay, well now I want to actually do the transformation. So this would be GA plus GB, GA minus GB, X plus Y, X minus Y, and then my Z doesn't change anything. Well, it looks like there's a whole bunch of G's in there. I bet I could just factor out a G. And I do. And I'm like, you know what? That kind of looks like my original transformation for ABC, which, as you probably guessed, that's my U vector. So now we're done. Cool. So that's a linear transformation. I know that kind of looks silly and repetitive, or just like, wow, you're doing so much work for something kind of obvious. Yeah, it is, but this is the process. This is what we're supposed to be doing. And you'd be surprised sometimes you think, oh, well, of course that'll work, but then it doesn't. So Be careful, okay? If something doesn't work, you're just stuck and it's not working, it probably just doesn't work. And that's okay. There are answers where it won't work. So we got transformation, a matrix, a 2 by 2 matrix, and we're going to a real number. So we're taking a whole matrix and we're somehow mushing it all together and making it a single number. What is something that does this actually is determinants. Determinants make a whole matrix turn into a single number, a single scalar. This won't be determinant, but I'm saying this is something similar to that. T of A, this is the definition of the linear transformation. A plus B plus C plus D, given that A matrix is A, B, C, D. Okay, basically they're saying my transformation, my function here is that I'm going to take all the numbers in a 2 by 2 matrix and just add them all together. Is that a linear transformation? So I tried to do this a particular way, and I failed. This is okay to try different styles. I guess I just wasn't realizing what to do with a matrix rather than just like some numbers. But it's really not too hard here. Just notice that it's T of A. And so instead of trying to do U's and V's and stuff, you're using a whole matrix here this time. That's what this is. Your input is a matrix. Output would be that. So you're not inputting a vector. You're inputting a matrix. And so really number one is now T of A plus B. And you should eventually make this thing equal T of A plus T of B. Notice that there's no actual vectors involved here. And that's okay. Can I do this step? That's the problem, I guess you could say. Really, what I need to do, A is already defined. I'm going to just predefine my B again. So E, F, G, H. Okay, awesome. So if I were to add these, forget about this for a minute. That's our goal. I'm starting here. What would A plus B look like? And so it would look like A, B, C, D plus E, F, G, H. Well, then what does two matrices added together look like? A plus E, B plus F, C plus G, D plus H. Okay, so we got it all combined together. What's the actual transformation? Like here, I got to actually get rid of my T. Well, it's adding it all together. So A plus E plus B plus F plus C plus G plus D plus H, all added together. Well, everything is added. You don't need to use parentheses, so I'm going to combine it the way I like to. So A plus B plus C plus D, and then plus on the other side here, E plus F plus G plus H. I'm saying this one, this one, this one, this one over here. This one, this one, this one, this one over there. Picking sides for a team, basically. And you can pick whoever you want. I choose this way. I just want to do it this way. That's my decision. Oh wait, you know what? This kind of looks familiar. I think I've seen this before. This is T of A, isn't it? Right there. Oh, look at that. We already got B defined. You know what that is? That's T of B. Now I might have skipped just a tiny bit here, but I mean the point is that we could see it's obvious that it's going to work. Okay. Let's keep going. So then I'm going to say T of. I already used a little C. Hi, I guess I'm going to use little I. It's my scalar. Just running out of letters, basically. So if I do I times A, I should be able to make I times T of A. Like that. Again, this is my goal, so I'm going to get to that in a minute. Let's start with this. So what does it look like to have I times this matrix? A, B, C, D. And of course, now I can distribute that I into that stuff there. It's almost a little silly to do this. AI, BI, CI, DI, and that's okay. It's a little silly, but we get the idea. This is what we're supposed to do. What's the actual function, the transformation here? AI plus BI plus CI plus DI. You just add them all together. Oh, well, you know what? They got a lot of I's in here. I bet I could factor out an I. And then, of course, I'm like, oh, you know what? This kind of looks familiar. I think I've seen that before. That's my T of A, isn't it? And again, I skipped like 2 steps at the end. I really probably should do this. And I'll show you. I'll just do it the long way this one time so you can see what's going on. Oh, you know what? That's that looks like T of A. And you're like, oh, but you know what? It's actually defined as like capital A. And now we're done. Yeah, either way, I'm not picky about that. That's obviously you know what you're going for. Okay, so those are just examples. I actually haven't done any proof stuff yet, and I do want to do a proof in this section as much as I can. So let me actually do like the proof now. So here we go. Let's define T as a function going from a matrix n by n, so it's a square matrix, going to a real number. So this is something we just saw a second ago. T of A is equal to A11 plus A22 plus ... all the way out until ANN. You know what's kind of funny? They even say this on the particular problem in the book. They say this is actually equal to the trace of A. So this is old stuff. We've seen this before. Just add up the diagonals. It's called a trace. They're saying prove that this, that the trace of A is a linear transformation. I'm just going to do LT. Makes it a little quicker there. All right, so what do we do? Well, just like the last one, we need A plus B. I guess I haven't defined what A and B look like, but I'm just going to do a sloppy proof, because that's okay. I mean, as long as you're getting it correct and you're understanding the steps, it's not like I'm cheating here. A plus B, what would that look like? Well, it would be A11 plus B11 plus A22 plus B22 plus ... I should probably use the ends, but it's not a big deal. Notice that I'm saying these two matrices are added, and there's a lot of steps in between here, but I say that the diagonals are basically going to be the two numbers added, and then I'm going to do the trace of it. Well, I could split this up as A11, A22, ... and then B11, B22, ... Well, you know what that looks like? You know what that looks like? That's the kind of the point here. This is T of A, and then plus T of B. So we're done there. Notice I'm doing a dot. I mean, I guess you might want to do a square there. I do the square at the very end of the whole problem. Dot, period, we're done with that statement. Let's move on to the next one. It's not like it's finally proved. That's kind of why I'm not doing it there. Personal preference, probably. So I'm just doing my own notation here, and, well, you're living through it, so there you go. So I need to do a scalar C. Again, do I have to predefine it ahead of time? I'm doing a sloppy proof here. It'll be okay. C times A11, C, A22, ... Well, hey, look, there's a lot of C's, so I bet I can factor that out. Wow, look, that looks like the transformation. Okay, and now we're done. You know, I'm not going to actually do that. Here, I'm going to write it. I'm going to do sloppy proof up here, but formal proof at the very end. Therefore, 3 dots. Therefore, T is a linear transformation. And now I'm done. Okay. Kind of sloppy proof and, well, formal end. There you go. Okay. 6.2. Moving on. This one's talking about the kernel and the range of linear transformations. A lot of this will be kind of familiar to you because we've seen this language before. So let me give you the definition of the kernel in particular. So let T go from V to W be a linear transformation. So, like, I want to say that we already have this is a linear transformation. We've already confirmed that number 1 and number 2 have worked, okay? So then the set doesn't look very good there. The set of all V elements of, well, V such that T of V equals the 0 vector. So just don't think I need a comma there, is the kernel of T. And they just sometimes specify this as kernel of T, K-E-R of T. So what does this mean? I'm saying the set of all my vectors such that I get this thing, that's my kernel. My kernel is a set of vectors, okay? I'm sure there's a fancy way to look at it, but I'm saying the V vectors here are the kernel. This guy right here, that's the kernel, as long as it results in a 0. Well, I mean, consider right quick. What about, like, you put in a 0 vector? Shouldn't you get, like, the 0 vector out? Well, yeah. This is called the trivial solution. We've already seen that a few other times. Trivial solution. This is nothing to write home about. This is okay, great, good job, awesome. Single number works, cool. I think that might be a property somewhere in the book. That's not really what we are talking about. So there might be some other ones out there. If we had the linear transformation somehow have, say, like linearly independent vectors, you know, like it's a matrix constructor with those, then perhaps it's only the 0 vector, only the trivial solution that will actually have that happen. And there's a lot of little proofs and stuff and theorems in this section about that. I'm not going to write them all up. I just want to show you like an example of what's going on here. So this is just an example of what to do. So 622. So we have R3 go into R3, okay? And so that's going to be a vector going to another vector. And so my transformation xyz is equal to x0z. Okay. So find the kernel of T. Find all the vectors that will make this equal 0, 0, 0. That's the goal. This is actually supposed to be 0, 0, 0. Can you see the kind of connection there? And so my goal is to say that x0z, the end result, is equal to the 0 vector, 0, 0, 0. Well, when does this happen? Well, this is when x equals 0 and z equals 0. Notice nothing about y. They're not talking about y there, are they? So the kernel of T would be all the vectors that look like this. Notice my x is 0, my z is 0, my y is anything. That's what this is saying right here. Any number. Y is any number. Doesn't matter because it yields a 0 regardless of what you have there. Put a 5 in there, it'll be a 0. Put a 7 in there, it'll be a 0. Put a -2 in there, it'll be a 0. So it could be anything. In a way here, I'm saying that we actually have dimension now. It's not just the trivial solution. We have actually like a dimension. So multiple answers. Okay, let me give you some more definitions here, okay? So these are more like definitions. We got the range of T is the set of my transformed vectors, not just the vectors, the transformed vectors. My image, I guess, is another way to say that, or my range, given that we have a vector in the original V. Okay, so like this is equal to W. This is where I'm going to. I'm going from V to W. Talking about the W guy. I'm going from X to Y, right? X values going to Y values. My f of X goes to Y value. Okay, so that's kind of the point there. So that's my range. We've seen and heard it, but now again we're seeing it again here in linear algebra. So the dimension of the kernel of T is equal to the nullity. I think we've seen that before as well. The dimension of the range of T is called the rank. Again, we've seen that before as well. This is way, way back in the day. Some other things, we got rank of T plus the nullity of T is equal to n. Like an m by n matrix, that kind of thing. Cool. Number of columns, I guess you can say. There you go. Number of columns. So let's keep going. We've got some more definitions. We've got 1 to 1. Now, this is sometimes abbreviated in like further books. as like 1 to 1, something like that. I'm not going to do that. I just think it's weird. 1 minus 1. It's not 1, 2, 1. That would be funny though. It's the different 2. That was just a math joke. So we got. Let me just give you like a graphical representation of what 1 to 1 is. Let's say we have our V and we have our W. We have our domain and range. And we got some values going from here to there, like this. There you go. Okay. This movement is T. It's a transformation. You're going from your domain, you're going into your range. Your range is all these values. But notice 1 to 1 is that for every one x, there's one y. For every one y, there's one x kind of stuff, okay? So 1 to 1. They also state in this section that the kernel of T would be only the 0 vector, that trivial solution, when you have a 1 to 1 transformation. Okay, so that's something to kind of keep an eye out for. Another word that we're going to see is onto. So onto is when the range of T is actually equal to W. And what I'm trying to get at is that like every element W in W, it comes from my V through T. So like I'm saying all of the numbers in W have been accounted for. My range, all of the range is, all of my my values there. I guess graphically what I would what I would say graphically, like as a not onto, here's an example. 1, 2, 3, 4. So this one goes here, this one goes here, this one goes here. Uh-oh. There's nothing for that guy. So he's not onto. Okay? This could also happen if you have 3 and 3. You go this one here, and this one here. Well, then this guy's left out, so it's not onto. But also notice that these two went to a single answer, so it's also not 1 to 1. Okay, so that would be not 1 to 1 and not onto. Okay. I don't want to go and show that too much. It's more of a focus of what it is, not what it isn't. And last little definition here, if T is 1 to 1 and it's also onto, so if it meets both of these, then T is an isomorphism. Isomorphism. That's a big word. You could use that at the dinner table. I learned about isomorphisms. So it's just a fancy word for saying 1 to 1 and onto. This is actually going to come up in different classes for you. I mean, this is advanced math. You're not taking this, unless you're actually going to go on to do more advanced math proofs and whatnot. This is going to happen in your life again. You will see that again. Okay. I don't think I should put a line there, but regardless, we're going to be doing an actual answer. It's not a proof, but it's something close to what the quiz has. So we're going to just do it here. And I'm just going to describe it to you physically. Okay, this is more like a physical problem. So I got my A matrix is a 0, 4, -2, 0, 3, 11. Okay, and they're saying that my transformation of x is equal to ax. So again, I'm just saying that my transformation is from one vector land to another. I'm going to take a 3. I know that looks terrible. And I'm going to multiply it in, and I'm going to get out a 2, a and b, let's say. Okay, so that's kind of the idea here. I'm going from a 3 to a 2 and all this kind of stuff. Well, it's represented by this matrix, okay? What we want to do is find the kernel, the nullity, again, that's the dimension of the kernel, the range, and the rank, which is, again, the dimension of the range. This goes to this, this goes to that. Let me show you the process of how to find all this. This is actually the first ones I'm going to find are these guys here. They're actually super fast and easy. What you want to do is you want to RREF your A. So row reduce it. And I'm just going to give you the answer here. It would be a 1, 0, 11 over 4, 0, 1, negative 3 halves. Okay. So I row reduce it, RREF, use a calculator, don't do it by hand, please. That would take forever. But I want to physically see what's going on here. Notice that I have two columns that kind of look like the identity matrix. Now, I wouldn't want to say that exclusively. What we're looking at more particular is the leading ones. Okay, the leading ones. So there's a 1 there, there's a 1 there. In opposition, let's just say I had a 1, 2, 3, 0, 0, 0. Well, how many ones, leading ones, do I have? I only got the 1. There's nothing down here. So do you see kind of what I'm saying there? I'm saying you can look for this, I guess, style here that's similar to I. But even then, what if you had a 2 right here? I would still count them. It's not the point of it being literally 0 and 1 only. I'm saying the fact that there's the leading ones. But it's kind of obvious to see column-wise that we have 2 of them. Okay, so that's going to be my rank. That's my rank is equal to 2. Okay, so that's easy. Notice that we have this column here that does not have a leading 1. Again, it's that dependent column, I guess you can say. And so this is your nullity is equal to 1. There's only one column like this. So again, 2 columns that rank, 1 column nullity. And so how is that going to work out in the end? Well, rank plus the nullity, 2 plus 1 is equal to 3, which is your n. That's your, again, it's a 2 by 3, right? This is a 2 by 3 matrix. 3 is your number of columns. So I should probably write columns here. Okay, cool. Okay, so verified there. Basically, we got this guy, check. Got this guy, check. But now we have the dimensions. What does actually the kernel look like? What does the kernel actually look like here? So using our RREF, I'm going to rewrite this now in terms of like x's and stuff like that. So x1 plus, and I'm going to leave a little bit of space. This is going to be helpful to us. Plus 11/4 x3 is equal to 0. Remember, I'm going to be looking for the kernel, and remember how the kernel is whenever you have t of v equal to 0. So I'm setting this whole thing, whatever I'm going to do, this matrix stuff, I'm going to say equals 0. And so in a way here, it's like I'm doing an augment with zeros kind of stuff, okay? So that's a way to consider that. So equal to 0. And then if I'm looking up here, that was, again, x1 plus this guy, x2 plus, again, that x3. So negative 3 halves x3 equals 0 again. I'm just rewriting this in terms of x1, x2, x3, x1, x2, x3. Well, this, of course, yields that my x1 is equal to a negative 11/4 x3, and my x2 is equal to a positive 3 halves x3. What is x3 equal to? It's not 0. No. It's not 1. It's not infinity even. No. It's anything. It's x3 equals x3. I know that sounds kind of silly, but this right here is actually pretty important. We did this back, hopefully you did this back in College Algebra 1414. But again, this has been forever for you, so I'm not going to just say, oh, of course you remember this stuff, dependent matrices and all that kind of stuff. Instead, let me just rewrite this. Instead of saying x3, because that's really tacky, I'm going to say instead that my kernel, let me try to rewrite that there, my kernel of t is going to be like a c value. And then my actual vector here, negative 11/4, 3 halves, and a 1. What's the coefficient in the front? There's a 1, actually. Again, you could make it all fancy, but at this point, it's not a big deal. Okay, so there's your kernel. So far we've got the kernel, check. Got the nullity already. Range, I don't have yet. And then the rank, yes, I already have that. So what's the range now? So the range, if you go and look at the book, they say this is also equal to the column space. So the range is equal to the column space, and what does that really mean? Well, it's honestly, I thought it was kind of weird, but this does work. The columns, physically, the columns that were involved in your rank, you're going to go back to the original and just pull those. And you're like, wait, I'm not doing anything with it? Nope, you're not doing anything with it. Just they're columns, column space. These were the ones that worked. These columns are great. This guy's dependent. You don't need that guy. It's not part of your column space. And so I would just say, what do we got there? 0, 4, comma, -2, 0. These here should be linearly independent. Notice because, I mean, well, you could just see it right here. They are linearly independent. But there you go. Cool. Columns that have a leading one, the ones used in your rank, these are the ones that you want to use. Okay. Moving on, next section. Here we go. 6.3 is matrices as linear transformations. You know what's funny is that we already did this like a couple times. So I'm going to just show you again what they're trying to talk about. You can rewrite your transformations as a matrix like this sometimes. Cool. That's basically the entire section. They do have a small point. They have that some big transformation could be broken up into smaller transformations. And then therefore you can also use your matrices similarly to get the same result. Okay, they sometimes, and I think on the quiz I even use like a little circle to indicate this composition is what it's called, composition, and that's cool and all. I actually would define it for you. Hey, look, you know, just a reminder or something like that, because just putting a circle here is very vague. That might be okay for college algebra because there's not a lot of different things with a circle in between, but here we got like circle plus, and we got circle times, we got a plain old circle, and we got like a circle with a dot, and I mean there's a ton of circles, so I would not just assume that you just know that, you know, without some English. Okay, 6.3.43. I'm actually doing two different problems here because there's not really proofy problems. It's more hands-on, I guess, so let's do that. So let t be defined as p2 to p3. Now what p means is polynomial. Polynomial, you know what that is. It's something kind of like that. So p3 is cubed and stuff like that, I'm pretty sure. No, you know what? Yeah, I think so, yeah. It means cubed, and that's p2 means squared. Yeah, okay, we're cool. Sorry, I was just looking at my notes, and that makes sense now. Now, this is definitely a linear transformation. So the above hold my two steps that I've done. Just, it is a linear transformation. Cool. And it's defined more specifically as t of p is equal to x times p. Now, this little p is polynomial. Again, this is a capital P. This is a little p. They mean polynomial. They're like shoving a whole entire function in here. That's like, that little p is like all the stuff, and then we should get out something else new. Okay, sounds fun. We have our bases, not bases, not basis, bases of our original b is the set of 1x x squared. You can kind of see this as being my like p2 business here. Oh, sorry, p2. While my b prime, this is basically my image. This is my range where I'm going towards. Should be the 1x x squared x cubed. Okay, there we go. Again, that's my p3 business. So I'm going from this to that, and I'm doing it with this guy right here. Now, it just looks so basic. XP. What is that? I don't know. Well, I mean, what they're actually saying is x times p. I know that sounds really weird, but my t of b should actually be then, this is, let me just make it more basic, and this is bad math. This is bad math. I'm going to say that, okay, right here. I don't do this all the time, but I want to just show you what in effect is going on. I got x times the 1x and the x squared. X times my p, xp, okay? Cool. So I'm putting that in there. so I'm not going to keep it because, well, that would be too official. What does x times all that stuff mean? In fact, I think maybe this would be an okay notation. I'm going to leave that. That looks cool enough. It'll be fine. So then you distribute it, essentially. And so now I've got x squared, and x cubed. Cool. Compare with this one. Look, see, we should have got to this. We got this guy instead. Very close, but not exactly the same, okay? What's going on is that on my B prime business, which I'm just going to rewrite for your edification here, if that's okay. X cubed, same thing. That 1 is not there. It's just gone. So I'm basically having to get rid of it. Zero it out. It's gone. I need to get rid of it. I know that sounds kind of weird, like, hey, how do you just get rid of it? Well, you zero it out. We didn't get it. So how do we get rid of that thing? So what I'm really wanting to do in this, like, what are we trying to do with this problem? They're wanting a matrix that's going to represent this movement, okay? So my A matrix is going to be, and this is kind of weird, let me just go ahead and give you the answer, and then we'll go from there. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Awesome. There's your answer. You're done. Well, wait. What just happened? Well, okay, notice here that I'm putting in a 3, right, x, y, z, and I multiply it, and I should get out a 4, okay? So I'm actually going from 3 variables to 4 variables still. This is good. This is good. I like this. Okay. But notice that my result didn't have that 1 in there. So what's going on is that I'm trying to, say, multiply by the 1x squared, and I should be getting out of this 4 numbers, but the top one's a 0 because it's gone. Okay, there you go. How do I get that 0 up there? Well, I just basically have the top zeros. Just blah, 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 0, boom. It's going to be 0 all the time, so I'm zeroing it out. But notice here, I got a 1 and a 1 and a 1. What I'm saying is when I multiply this in here, I'm going to get this x result out of it, okay? You know, actually, I don't think I like my answer now that I'm kind of looking at it here. Because if I'm multiplying the 1 by the 1, I think, actually, I should kind of redo this. I don't actually have a very good answer, but maybe if I put x's instead right here? I kind of like that. I kind of like that right there. Also, another version that could happen. Here, I don't like this answer. Now that I'm kind of looking at it, I don't think it's right. And it's kind of off the fly because I kind of was just looking at it like, oh, that's perfectly fine. But maybe it's not. So let's just analyze this here together. This is my goal. Here, let me rewrite our goal here. And this is okay. This is okay whenever I don't get it perfect, you know what I mean? I'm very sure that the top is zeros. That one's easy. And again, I'm putting in a 3, and I need to get out of 4. So I got 1, 2, 3 more things. If I put this in here, I need to result in an x. So how do I do that? Well, notice that if I put a 1 right here, and I multiply that x times a 1, I should get an x right here. What I often see this as is something like that. It's descending onto it, and then it just spits it straight out because it's plus, plus, plus. Well, notice here that I'm resulting in an x, okay? When I'm multiplying this guy in and I want to get an x squared right there, I just get one of these guys here. Cool. How do I get the x cubed? That's the weird part. And I would almost say, and this is strange, maybe this is wrong or not, I don't know. I'm going to put an x here. Because what I'm doing is I'm saying, hey, I just put another x on there to get the x cubed. And technically another version that I think would work fine is if you used x's here as well. Okay, so that version also works. And we're using a ton of x's anyways, might as well put some more in there. It never really specified that the matrix had to be numeric. So this is okay, I think. I'd have to look at this one a little bit more. I think that's kind of weird, but it still works. This also works for sure. Different ways to answer this, okay? Let me show you the other one. Okay, so we got T1 is defined using xy equals, and so x minus 2y, 2x plus the 3y. And I'm going to do the T2 here in just a second. Let me redefine this using matrices. So A1 would be equal to, and notice here I got x's and y's. Scalar-wise, I got x times the 1, 2 plus y times the negative 2, 3. I'll just pause for a second. Notice I got a 1x right there. So how many x's do I got this guy? 1. How many x's right there? 2. Okay. So that's not too bad there. Yep. And then my y's, of course. My y's, y times this guy, y times that guy. Again, this is a, if you can't remember, this is actually a vector, but written horizontally. You see that? So I'm just taking this guy and splitting them up. And splitting it up. Okay, awesome. I don't want to keep that up there, though. So I got my matrix A, kinda. Notice again, it's not like perfect or nothing, but if I wanted to put this into a 2x2 matrix just to like say, hey, this is a 2x2 matrix, and I'm going to multiply stuff by it, well, then that'd be a 1, 2, negative 2, 3. Because then I could just multiply by xy and I get my answer. Okay, so let's just say that like my A, numerically, would be that guy. Same thing for T2 here. We got a y and then a 0. This one's kind of different. So I got my A2 would then be x times, well, 0, 0. How many x's did you see in there? None. Where was the y? It was only one y, and it was in the first category. And so if I were to actually do like a matrix, I guess it would be this guy. Cool. So the point that they're trying to make here is that what if I had T1, T2, x vector? Well then, like we saw before, that's A1, A2, x. Could I multiply these a's together to make my final t? What about my T2, T1, x? Well, that would be the, again, this is x vector there. A2, A1, x. Cool. The goal here on this particular problem is just find out what the big A matrix is going to be, depending on what's going on here. So A1, A2. I think my A's are getting kind of sloppy. Well, A1 we know is this guy. And A2 we know is this guy. Now hold on. Hold on. What is this defining? Yes. Okay, yeah. It's A2, A1. Yes, this is good. My bad. I often get scared about the order of operations. Notice that when you're actually multiplying or you're doing transformation, does this one first and then that one, right? Composition. Same thing here. You're going to multiply these two and then you're going to multiply those two. So this is good. The ordering is good. I do have the answer for this one. It'd be 0, 1, 0, 2. So there's one of your answers. A2, A1. Again, you're just setting it up. Same thing. And this results in 2, 3, 0, 0. Awesome. So there's your answers that they're going to ask for, blah, blah, blah. Moving on. Last section, I think. No, we got 2 sections. But the last one's like super, super fast. So 6-4, the last big section. This is transition matrices. I don't know what that was, but that's fine. Similarity. That's what we're really going to talk about. Similarity. That's the big topic. So if you have square matrices A and A prime, order n, so like n by n matrices basically, A prime is similar when there exists, there's my backwards E, I don't use it a lot, but there exists an invertible matrix P, try to write that a little bit better, P, such that A prime equals P inverse A P. This is the definition. I mean, there's really nothing else to it, but let me talk about it before we actually keep going. So similar. Similar matrices. You got your A prime and you got your A. These guys should be, again, keyword here, similar, because it looks kind of like I got a P inverse and a P. Let's just do some basic numerics on the side, okay? I'm going to choose 2 and 3. This is going to be kind of weird. So 2 is equal to, or 2 prime, or whatever you want to call it, special 2 is equal to, let's do the inverse is 1/3. My original was a 2, and then my P would just be a 3. This is just silly math on the side. Not bad math, it's silly. Notice that the 3 and the 1/3 are going to cancel. So does 2 equal 2? Yeah. That's the kind of the point here, is that finger quote, they cancel. Now, they do not cancel. They don't. This is only for scalar, real numbers here, okay? That was just a show of why they're called similar. They're not actually equal. They're just similar because, the dimensions and stuff, and, well, that's just their term. But they do not cancel. It's just, I'm saying, that's kind of the idea behind it, okay? 6, 4, 35. Now, this is actually a proof problem, finally. So, prove that if A, and B are similar, then A transpose and B transpose are also similar. We're saying that we know for sure A and B are similar. What about A transpose and B transpose? Are they similar then with one another? Well, so we're going to do a proof. So suppose that we actually have this similar stuff. I'm going to do A is equal to P inverse B P. Okay? I mean, that's the top statement. Prove that if we got this thing, so there you go. Then, so now I'm going to prove all this other stuff here. So to prove that A transpose or B transpose is going on here, what are we going to do to all this stuff here? Well, I'm going to transpose it. I'm going to transpose both sides. And this is where the fun math begins. So I transpose both sides. I just got to do something to it, right? So over here, obviously we just have A transpose. But over here, it's kind of weird. You have to go way back, and this is kind of on the side. Actually, I don't want it on the side. I want it to be part of the real proof here. So I'm going to write out some English with every step, just as a reminder. And I'm going to do this with a couple problems coming up here in this chapter and the last, okay? Because they're old stuffs that we're going to have to remember back in the day. So I'm going to rewrite this as P inverse BP still transpose, okay? And now I'm actually going to rewrite it as BP transpose P inverse transpose, because, like, as in, we know that, and I'm going to have to use different letters. Let's use C and D. C and D transpose is equal to D transpose C transpose. This is like part of my proof. I'm just reminding myself where this came from. This is back in chapter 2 or something like that, where when you transpose a product of matrices, you just flip them. You flip the inside. That's how you kind of distribute your transpose in a way. Okay, and I decided, associative rule, to make these two together. Okay, I just decided that they look cool together, and they all work together as well. I did something different on my paper, so it doesn't really matter. Whatever you choose, just associate them together somehow. Well, again, we can now say with this guy here the same thing. So PT, BT, P inverse T. Okay. You don't have to write the rule every time, but this is the same rule. I'm just basically distributing this guy, just like I distributed this one here. I'm now distributing that one there. Now, you might think, well, couldn't I have just, like, done this from here to there? automatically. I guess. I don't know that rule. I just, it somehow ended up this way, so that's fine with me. And so far, what we have, and I'm going to try to clean this up here, we got this guy here. Okay. Now, it's similar. It's similar. It's, I don't want to say that word similar. It's, they're pretty close. We're pretty close to an answer, but it's not quite there yet. What I need to do is somehow reconfigure this guy, because it's not happy that way. And so I'm going to say now that I can actually change this to be transpose inverse. Because, and on the side here, C inverse transpose equals C transpose inverse. And again, that's back from chapter 2, long time ago. Okay, I'm just reminding myself why I can do this step. So I'm able to switch them out. So that's good. Okay, so I'm going to say let my PT equal Q. Just making some random letters up, P and then Q. So then I now have AT is equal to Q BT transpose, B transpose, Q inverse. Now look at this guy. That's the definition of similar. Now, pause for a second. Did you see something that's a little different here than what the actual definition was from the book? Just a little tiny difference. Scroll up for a second. Here we go. Notice my definition has the inverse first and then my original. And yet, down here, I have the original and then I have the inverse. I'm going to tell you that it does not matter here because I could just say, okay, we'll let what's after P is R, or PQR is Q inverse. And so then I literally could just rewrite this as R inverse B transpose R, and then we're fine, right? It doesn't really matter. We have some, that's the word up here. There exists some P where this will work. Do we have some matrix that's going to make this thing work? Yes. So we're done there. We proved it. Okay, last section. This is super, super fast. It seems like almost always the last one's always applications. So applications. I have nothing new to talk about in this section. I'm just going to do one that's kind of similar to the one in the quiz. So not the one on the quiz, but something similar. We're going to be taking matrices and rotating them. So I'm going to need to rotate a 3D vector. I know it sounds kind of weird, 3D vector. We don't need that. An R3 vector. There, that's a little bit better. We want to rotate it 45 degrees about the z-axis. Then, pretty important that then right there, then 135 degrees about the x-axis. So I'm going to take a vector and I want to rotate it this and then that. So how am I going to do that? What's my transition matrix for that kind of stuff? So you have to go to the book, and they have 3 different varieties of matrices here. What you actually want to do is you want to have the z-axis one come over here so that you can multiply it by, I don't know, some kind of vector. And then you're going to multiply it here by the x-axis matrix, okay? This one first, and then that one, okay? It's kind of composition backward stuff again, right? Well, let me go ahead and fill these guys in here because there's like a whole lot of stuff going on. But this is like the meat and taters of what's going on. You're wanting this part. That's kind of like the answer. On the quiz, I put one of these 1, 1, 1 vectors just so that you can have something to multiply it by. And just to get like a number, it just seems more applicable than just what I'm going to do here. So the x-axis and the z-axis have very particular shapes. Again, this is straight from the book. 1, 0, 0, and then 0 is going down. This is going to be a cosine of the 135, negative sine of the 135. Do I really have to put degree symbols? Are you okay without it? Cosine of the 135. And then times, again, this is my z axis matrix stuff here, cosine of the 45, negative sine of the 45, sine of the 45, cosine of the 45, and then 0, 0, 1, 0, 0. Okay. Again, on the quiz, I think I give you a 1, 1, 1. You multiply it and you give me a new answer, whatever that is. Okay, that's it. We're done. Thank you very much, guys. Have a great day.